So we just talked about a few different rules that can help us simplify some statics problems. So quickly run through those. If you've got a rope or a bungee or a chain, anything flexible, and you apply a force to that, let me just exaggerate this a little bit more. You apply a force to that like so. Then the rope will always stretch, it'll straighten out, and then it'll also move to line up with that force. So it would straighten out and move down there. And you can use that fact if you're given a problem that's got a particle and it's got some ropes attached to it, then you always know the reaction forces are always going to be aligned with those ropes. So the forces in the ropes, the line of action must follow the direction of the rope or cable or sling or bungee. The next one is pretty similar. If you've got some structural member, so it might be a box section or a I-beam or an angle or anything like that, and if it's got pinned connections, so we looked at what those were, it's got pinned connection, the same thing will apply. So if you apply a force at an angle, because it's pinned at both ends, and it has to be both ends, because it's pinned at both ends, that's free to line up with that force. So the force will align with the direction, or the member will align with the force. And similarly to ropes, works in the opposite direction. So if you've got some particle here, so we've chosen a particle there, and it's being supported by structural members, structural elements that are pinned at both ends. What colors am I using? Then the forces will always align with those structural members. So it's only true if they're pinned at both ends, not if they're just pinned at one end. Have to be pinned at both ends. So that was that one. Then we also had pulleys. So if you've got a pulley like so, and you've got some rope over the top of it, and the pulley's attached to something, then the tension force here, if you ignore the friction in the pulley, will be the same as the tension force there. So the force doesn't change as it goes over that pulley, as long as you assume there's no friction. And the last one was the one we're going to use here. If you've got some object that can roll, so anything circular really, and it sits on a slope, let's make it something you can see. We'll use 30 degrees, say. Now obviously it wasn't attached to anything, it just rolled down the hill, but you're usually assuming that it's attached to something, so it can't roll away. Then you'll have gravity will always act straight down. And the reaction from the ground is always at 90 degrees. So let's have a look, what was this? This was 30, wasn't it? And so if I want 90 degrees, I'm going to have to go past 0 and then go 60. So the reaction from the ground, do it in a different color, is always it's always perpendicular to the surface. So it's at 90 degrees. So this angle here is at 90 degrees. Okay, so there are just a few rules that you'll see when you're doing these kinds of static problems, and we do actually use these rules. It's not just a construct to make life easier for these problems when you're first getting started. When you're analyzing engineering problems, often you'll make some simplifying assumptions, but you just have to be careful that those assumptions are reasonable. So it's not reasonable to say there's no friction in a pulley, but it is reasonable to say it might be very small compared to the forces. Similarly, when we're talking about the ropes, so if you have a rope, imagine we've got something that's hanging, it's got a weight hanging from it, and it's fixed here, fixed here. Now, that'll be true as long as this weight here is much, much heavier than these two ropes. But if you're using really heavy chains, that rule wouldn't really be true anymore. What you'd end up getting, you'd have an attachment point here, attachment point here. You might be supporting a weight down here. What you'd find would be that this would have a catenary shape, what's called a catenary shape, but it would be slightly curved because of the weight of the rope. And so your reaction forces wouldn't be a straight line, follow the initial curvature of that chain. Sorry, did I say rope? Chain. So you have to be a little bit careful with the assumptions, but we do use them in real engineering problems. So let's have a look at this problem here. So we've got a roller. We're ignoring friction. That would only really be true if this was a pretty hard surface, but we're ignoring friction, and we're asked to find out, so the tow bar is this part here that connects the tractor to the roller. Now usually the tractor has a hitch on the back. If you're not sure what that looks like, Google it. But that hitch is basically a pin, and the connection to the roller is a pin. That's why the roller can roll. And so this here, if you remember, we had struts and ties. Strut is in compression, tie is in tension. This, between the roller and the tractor, this element is a tie. And so there must be a force acting in the direction of this tow bar. And we're going to have gravity. And so I'm usually saying let's start with the primary force, the one that's causing everything else. And in this case, that would be gravity. And then we're going to have also a force in the tow bar. Don't know what it is yet. And we're going to have a reaction from the ground. And that reaction is going to be at 90 degrees. So this time we've got 20 degrees as the slope. It's going to be at 90 degrees, so I'm going to come down to 0. Then I need to go another 70 to get my 90 degrees. And so the reaction from the ground, it's going to be something like this. And for all of these, I don't really know the length yet. I'm kind of trying to draw them as if I do. So we are looking for the particle we'll use for particle equilibrium. It's always, or usually, it's where all the forces converge, which in our case is the pin at the center of the roller. So we'll draw a free body diagram just of that particle. So it's almost as if we've pulled that particle out, and then we're looking at all the forces that are acting on it. So we've got gravity now. Just so I can do a bit of a scale drawing so I can check my answer, we've been asked to calculate to 3 significant figures. So a scale drawing is not going to be enough, but it is a good check. So the first thing we're going to have to do is we're going to need to figure out what is this gravity, and then at least we know one magnitude. So being given the mass, we want the weight. So weight equals mass times acceleration due to gravity. The mass is 3.5 tons. Gravity is 9.81 meters per second squared. Therefore, weight is equal to 3.5 times 9.81. 34.34. I'm just going to keep 4 significant figures from now on, just until I get to the end. It's just a bit more accurate. It doesn't really matter, but we'll do it that way. So you keep 4 significant figures until you get to your final answer, and then round it to 3. So we've put in tons here. So therefore this must be in kilonewtons. If we put in kilograms, it would have been in newtons. So we can now draw this first vector, and we know its magnitude, so we know what length to draw it. So let's do that. We'll just want to make it reasonably big, just so I can get something reasonably accurate out of it. And so we've been asked to calculate this to 3 significant figures. So a scale diagram is not going to give us enough accuracy, but it's always a good check, so it's always worth doing. So we'll do 5, 10, 34. So we'll do 10, 20, 30, 4. Just using my ruler, not the squares. 10, 20, 30, 4 kilonewtons. The other vectors, I don't know their magnitude at the moment, but I do know their line of action. So we're just going to, it hasn't actually told us in the question, but we're going to assume this tow bar is parallel to the ground. And therefore that tow bar is at 20 degrees. So we can draw on its line of action. And we know that the reaction from the ground is perpendicular to the ground. So it's 20, so that must be at, on my ruler, at 70 degrees. So we've got a line of action here. Let's just make sure we write those on. So that there is 20 degrees. This here must be 70 degrees to make those perpendicular. So the whole thing will add up to 180. This is 90. Therefore, these two must add up to 90. Therefore, this one must be 70 if that one's 20. Okay, you can't do too much more until we start playing around with some of those. So again, we're going to imagine putting these nose to tail. So we just imagine we've got a vector there. And so if we wanted to put that nose to tail, we'd take this one, 20 degrees, we'd bring it down here. And so it would head off in this direction. And we just wouldn't know, at the moment we don't know when to stop. And to get a zero resultant, so to get particle equilibrium, all the forces must cancel out. Therefore, if you're doing it graphically, you must come back to the start point. Therefore, we know that this reaction from the ground, when they're nose to tail, it must come back and its nose must be here. This pen looks awful thin. It is. So it must come back to here. And so its line of action is this direction. So it would come like that. And so that tells us how long this one would be. And then we'd have their nose to tail. So we'd have this vector here, nose to tail is here. This vector here, nose to tail, must finish up here. Therefore, it must be here. And so now we've got the magnitudes. And I could just rub out what I didn't need. So let's get the length of these. So that is 5, 10, it's about 12. Let's have a look at that. 5, 10, I would say 12 kilonewtons. So we'll just draw it on. So I'm drawing it back from the particle, from the point of application. We'll say 10, 12, didn't we? 10, 12, double check. Yep. 12 kilonewtons. 10, 20, 30, 1, 2.5, so 32.5. 10, 20, 30, 1, 2.5, 32.5. So we found those two forces using the graphical method. And so we were asked to determine the force in the tow bar. The force in the tow bar is roughly 12 kilonewtons, but we were being asked to get it to 3 significant figures. It's probably not accurate enough. And so we're going to have to do the calculation. So if this was a question in an exam or something like that, I wouldn't expect you to do this in so much detail. If you have time though, and you've already done it numerically, it would be worth coming back if you've got time at the end of the exam and just doing the scale diagram and checking you've got the answer right. And if you're doing this for an engineering problem, so when you start work and you're actually having to do some calculations, just to check, and even if you're a construction manager or doesn't matter what your role is, there'll be times where you need to just check some calculations to make sure things are safe or it's been designed correctly. When you were if you're doing this for a real job, it would also be worth doing this to check your answer, make sure you got the right answer. However, in this case, we're just going to do this numerically now. So let me see if I can copy this down. Now, so solving numerically, the first thing you should do is write down what's the rule we're using? So we know that we've got static equilibrium, therefore we know that every particle in this whole system must have particle equilibrium. So for particle equilibrium, what does it mean? It means that the sum of all the x components and the sum of all the y components equals 0. Now, because this one's a bit of a special problem and it's worth just looking through one example where this is the case, this is a shortcut. So you could proceed as usual. You could just assume the usual x and y axes. So y vertically on the page, x horizontally on the page, x and y. And then we'd have to find the x and y components of f1, write them in terms of f1, x and y components of f2, write them in terms of f2, and then use these equations to try and solve this and figure out what f1 and f2 are. But I think there should be a bit of a shortcut here because these two vectors are at right angles. So usually it'll make things a bit quicker if we use that for our x and y axes. So we're going to use our x and y axes this way. What does that mean? Well, it means that this here is now aligned with our x-axis, so it's only got an x component. And this here is aligned with our y-axis, so it's only got a y component. So therefore, we're just going to have to figure out the x and y components of this force. Okay, so how do we do that? We just, I'll do it in green. So x is this direction, y is this direction. Okay, and then we solve as usual. So just to reiterate, I've seen that these are at right angles because it's 180 take away 20 take away 70 leaves me with 90 for this angle. Probably a good idea just to put that on so anyone reading it understands why you've done it that way. And then I've just chosen these two, the lines of action of these two vectors as my x component. So this is the x direction. I've chosen this as my y direction. Why have I done that? Because it now means I only need to find the x and y components of one vector instead of having to do it for two vectors. So it'll speed things up a little bit. So this is x, and this is y. Okay. Now there's something else I'm thinking. What am I thinking? Nah, let's just work through it and we'll see. So let's find the sum of our x components. So f1x is just equal to f1 because it's in the same direction, is equal to f1. ft, the tow bar, x is equal to, so this one here is ftx, this one here is fty, and they're both going to be negative. So we're going from here to here. And so we're going to go in the x direction first, then the y direction first, then the x direction. So let's just put our heads on our arrows here so as to go that way and that way. So these are both going to be negative. So ftx negative this way. Now we need to know one of the angles in here. So let's have a think about that angle there. I know that's 20. The question is, how do I know that's 20? There's a couple of ways we could do it, but we know, you remember the x, if if you've got parallel lines with a line crossing, so parallel lines with a line crossing, you don't even need the parallel lines, you actually just need two lines crossing. This angle here is the same as that angle there. So we know that this is 70, therefore this angle here must be 70. I'm just going to write it, and then so we know that that there is 70. We also know this is 90 degrees because this is horizontal and gravity is going straight down. So the whole thing is 90 degrees. So this here must be 20 degrees. Okay, so you see these. How can I draw it? Let me just show you where the crossing lines are. So you've got one line here, got another line here, and so that's just the same. You've got an X shape, and so opposite angles are equal. So this here is 70. Get rid of those. Once you've got that, you know that what I'm drawing here is 90. So this whole thing is 90. So 70 plus, so 70 plus this angle here must be 90. Therefore, that angle must be 20. So that's 20. And so therefore, this is going to be too many colors. This is going to be opposite. This is going to be hypotenuse. Therefore, we're going to use sine. So ftx is going to be 34 sine, so 34 kilonewtons times sine 20 degrees, and we're negative, we're going in the opposite direction, so we're going this way, the x-axis is going this way, so this must be negative 34 sine 20 degrees. My writing's getting a bit messy. Negative 34 times sine 20 degrees minus 11.63 equals minus 11.63 kilonewtons. Kilonewtons. Okay, so we figured out the x components of everything. Well, no, we haven't, have we? We have. So f of 2 is in the same direction as y, so it does not have an x component. So therefore, that's all the x components. We're going to get quickly to the end here. So sum of f of x equals 0. Sum of f of x is just equal to fx. So sum of fx is 0. So it's just equal to f1. Let's write it out. Equals. So therefore, f1x plus f2x plus ftx must be equal to 0. And just to make it clear to anyone reading the calcs, I just want to make sure it's clear I haven't just forgotten about f2. So f2x equals 0. So therefore we have f1x is just the same as f1, it doesn't have a y component, so it's just f1 plus f2x is 0 plus ftx is this up here, plus minus 11.63, which is the same as minus 11.63. Minus 11.63 equals 0. Therefore, f1 equals 11. So added 11.63 to both sides equals 11.63 kilonewtons. Final answer now, so we can just go to three significant figures because we've got our answer. We don't even need to worry about the y components. 11.6 kilonewtons. We can underline that because the think it agrees with what we did graphically. Yep, 12 kilonewtons, so we're pretty close, 11.6 kilonewtons. Now, F1. Why does that help us? Because we're now finished this problem. It just asked us for the force in the tow bar. The force in the tow bar is F1, so we don't even need to worry about Y components. And that came out more quickly just because we did this. We lined up those X and Y axes. So have a look through it again. You can even do this question using the normal method and finding the X and Y components of all and see how it compares. You'll get the same answer, but doing that little trick saves you an awful lot of time. So we still haven't written down the answer yet. So what did it ask us for exactly? Determine the force in the tow bar. The force in the tow bar is 11.6 kilonewtons. Another long example, my apologies, but just want to take our time, make sure everyone can follow. Remember, when you're doing this stuff, you can just, if it's all very clear, you can fast forward. If it's not clear, let me know in the tutorial or come and see me in the consulting hour. We can talk through it again.